Okay, so welcome back to another video. So here today we have a definite integral from 0 to 2 pi of sine theta plus cosine theta quantity to the power n d theta, with the parameter saying that n has to be a positive integer. Now one can actually compute this integral and evaluate the bounds using the reduction formula, which is basically like calculating the integral using recurrence relations within the sequences. But we're not actually going to do that in this video. And I'm sure that you can find other videos of computing this integral using recurrence relations, but we're not going to do that, the reduction formula I meant to say. But we're actually going to be doing a little bit of a nice twist to this. So if you notice that sine theta plus cosine theta, that's my first takeaway on the first step, is that you can actually convert these into the exponential functions, and with those exponential functions of the representations of those actually contains the imaginary unit. So implying that we're actually going to be jumping into the world of complex analysis to actually evaluate this integral, which this is going to be very fun. You'll notice that, of course, we're going to have to do a little bit of some substitutions, and there's a couple of, formulas and theorems that we're actually going to be using. It all work in the world of complex numbers, so perfect for that. But the results actually comes out very nicely, and you'll see in a sec. So it also needs to take into account that for positive integers n, it's a slight possibility that they might come up. The result might split into two answers simply because of depending on how the integral is written. But we'll see what happens from there. So anyway, let's actually just jump right in. So we know that sine theta can be written as the following. We can say that this is just equal to e to the power I theta, subtract e to the negative I theta, then divided by 2i. And then cosine of theta can be rewritten as e to the power I theta. Add this with e to the negative I theta, and then divide this by 2. So with that, let's actually just make the substitution. I'm going to call this our given integral capital I. And now we just put in the substitution. So this is from 0 to 2 pi. And now this will be e to the power I theta, subtract e to the negative I theta, divided by 2i. Then subtract, then add e to the power I theta, add this with e to the negative I theta, then divided by 2, and then close this off to the power n, then d theta. Now, let's actually perform a little substitution. And so this substitution is going to be very nice because this is actually going to convert into a new form of an integral, which is covered a lot that I've done in the past before. And you can pretty much recognize where I'm going with this for anybody that can see where I'm heading towards. So if we let the following variable, we let z equals e to the I theta. So hence, we see that this is actually in the form of a complex number, hence the polar form. So if we differentiate both sides, so we have dz, I shouldn't put the equals there, I don't know why I did. dz is equal to I to the power, or I times e to the power I theta, then times d theta. Nothing we can really do with just the d theta itself with that substitution. Let's fix this up a little bit. Why don't I divide the I to the e to the I theta, both sides? And we notice that z is equal to e to the I theta, the polar form of that. So I'll just replace that with z. And so we see that d theta is indeed just equal to dz divided by I times z. And so from there, now we can actually make our little substitution. And don't forget, we have to compute our new bounds too. But this is very nice because, again, this is polar form. And then if we see our bounds from 0 to 2 pi, if we explore this into the world of complex analysis of the polar form, this actually forms a path. Specifically, this is actually going to form a unit circle, radius 1, the center at the origin. So that means it's our the absolute value of z equals 1 of our new contour integral of the following. So now our new I in this situation is going to be written as follows. So we have this circle over here. Anybody knows that this is actually dealing with contour integration. The direction along the path we're integrating is in the clockwise or the counterclockwise direction. That's known as the positive orientation. So we have our path being along the unit circle. We call this absolute value z is equal to 1. Then we actually make the substitution over here. So now we said z, then this will be subtract z to the power negative 1, or z inverse, then divided by 2i. Then we add this with z, then add with z inverse, then this is being divided by 2, and then this is still to the power n. multiply, or rather with d theta, we have to plug in a new substitution, sorry about that. This is supposed to be dz and then divided by I times z. Okay, so now from here we can actually do a little bit of substitution from the inside of our expression, the integrand. If you notice, well, let's take things one step at a time. Let's actually get a common denominator over here. And so if we have if we have 2i, then I'll multiply I to both the top and bottom. So we have I times z plus I times z inverse. I'll factor that I out, but we notice that we can also factor out and group it in terms of, both the z and the z inverse factors. And so by doing all this, and then also by distributing the exponent to n to both the top and bottom, so we actually can factor out some stuff out of our integral. So what you'll notice is that if I'm going too fast, you can actually see for yourself that take things one step at a time. You see that this is actually coming to the following results. So here we have 1 divided by 2 to the power n. Okay, that's because we just, after doing this whole butterfly method, get a common denominator. This is under 2i, so I factored that out. I can also factor out the 2i over here, so to the power n. But don't forget, we have a I divided by z from the bottom here, so I'll factor out that I, so that means we have a plus 1 over here. And now this is still our integral, contour integral from our unit circle, z is equal to 1. And so after doing all this factoring, so now we would have the following. So we have 1 plus I, and then multiply by z. Then add this with I subtract 1, multiply by z inverse, still all to the power n, and then divided by 2, or divided by z, since the z is coming from here. Sometimes I write my z's, they look like 2, so that's why I got that jumble mixed up. So far that's what we have, and I'll just underline in black just to make the establishment of what we have, so far achieved. So now we have to think, what can we do next? Because we have something to the power n, but all within that quantity. So we can actually now use the binomial theorem. And so the binomial theorem states that for some real values, or rather in the world of complex analysis, so complex numbers. So we have, so for x plus y to the power n is simply just equal to the partial sum. So the top index is n, and then k is equal to 0. And choose k, in other words, that's the binomial coefficient, of x to the power n minus k multiplied by y to the power k. And this is for n greater than or equal to 0. This is the binomial theorem over here. So now let's actually apply this. So when we move on to the top right here, so I'll say by binomial theorem, then we can write this, the inside expression over here. So 1 plus I times z, and add this with I subtract 1 z inverse to the power n. This is simply just going to equal this following over here. So we have the partial sum, I'll put this over here. So we have the partial sum, n, k is equal 0. Now we have n choose k, then we just substitute, these, values in for x and then our y. So now over here we'll have 1 plus I to the power n subtract k multiplied by z to the power n subtract k. Then now we just multiply this with I subtract 1 to the power k multiplied by z to the negative k. Okay, and now we can actually simplify this a little further because we have some z's over here that we can actually, combine together. So now this would lead us to say this is now the new partial sum. K is equal 0, n choose k of 1 plus I to the power n minus k. That hasn't changed. Then we just multiply the I minus 1 to the power k, then combine these two together. So this will be z to the n subtract 2k. Now going back to our capital I that we actually, that's our given from back here. Now performing that substitution, now we would have the new following. So we have 1 divided by 2 to the power n, then times n to the I to the power n plus 1. Of course, we still have contour integral from z of our unit circle of radius 1. And now we have the partial sum in our substitution. K is equal 0. Then write the same thing, n choose k, 1 plus I, then n subtract k, multiplied by I minus 1, then to the power k. And then we have a z on the bottom, so I'm going to combine this with the our z base right here. So it's a -1, so I'll add a -1 to the exponent. So this will be z n subtract 2k and then -1 dz. Okay, so far so good. But I think it's also worth noting that we noticed that our f of z function is actually has a pole at z equals 0. So let me actually put this over here and say z is equal to 0. What does this imply on what do we have to do now? Well, we can actually jump in and say that we can actually apply the residue theorem. But before we get to do that, because we have to deal with this partial sum over here. So how do we actually go on and take this out? Well, we can actually use what's known as the Laurent series, which is basically dealing with the formal power series, but we're dealing with negative degrees as well. I'm also just going to write the formula on what the Laurent series is supposed to establish. So I'll say it like this: for a function f of z whose Laurent series is about a pole z sub 0, in this case we have z is equal to 0, then f of z is, this is the expansion to say of the Laurent series. This is supposed to be the infinite sum at n is equal to 0 of a sub n, then multiplied by z, then z sub naught to the power n, and add this with the partial sum, well, the infinite sum. Then we have n is equal to 1 of b sub n, then multiplied by z, then in z subtract z sub naught to the -n. And the a sub naught and the a sub n and b sub n, those are coefficients that's actually computed from the Cauchy integral formula. I'm not really going to go too much about that. So if we have this Laurent series expansion, then that means that the residue of f of z, so I'm going to write it like this: the residue of f of z at z equals z naught. In other words, I can write this as the residue of f of z, then comma z naught, is the coefficient, so COEFF is the coefficient b sub 1 of term 1 divided by z minus z naught. In this case, our situation we have is the poles z is equal to 0, so now that would be 1 divided by z. Z is equal to 0, I'll put it like that. Okay, so now we have to do a little bit of analyzation. So if we look at our z from our f of z function from this contour integral over here, we know that the term occurs for where is it? N minus 2k minus 1 is going to equal -1. Okay, so let me write it like this: term occurs when n subtract 2k minus 1 is equal to -1. All right, and if we solve this out for k, that's our our index, then we see that k has to equal n divided by 2. Then there's some things we need to pay attention to. Remember, we have dealing with positive integers, so we want to consider both the odd and the even numbers. So let's actually make the analyzation. So for n is odd, then that would have to mean that k equals n divided by 2. It can't be an integer, and that's not going to fit in our index, since the index always deals with natural numbers, or in a situation we're also including 0 as well. It's not an index, then that would have to mean that no term exists, no term for 1 over z exists for odd n, and so therefore we say that the residue of f of z 0 is equal to 0 for odd n. So that's one. So now we have to consider the even numbers. So let's actually make that observation. So when we say that n is even, then we know that indeed k is going to be, k equals n over 2 is definitely going to be an integer, because obviously we know that 2 can divide into any even integer. So n divided by 2, that is indeed an integer. And so implying that indeed can be an index, and so that means the term 1 over c for even n exists. And so for that coefficient of that term, all we have to do is just plug that 1 over n back into our coefficient over, the term 1 over n has to plug back into the coefficient over here, specifically this thing right here, not including the z function. So if by doing so, then by plugging this back in, so we now have, plug this in, so n choose, instead of k, this is going to be n divided by 2 of 1 plus I, then to the power n divided by 2, then I subtract 1 of n divided by 2, okay? Now, if we actually simplify all this out, you can actually just apply the FOIL method of all that to the n divided by 2, and then simplify all this out. You're going to get now, well, not in complete simplification just yet, but what we have so far, this is just n choose n divided by 2 of -2 to the power n divided by 2, okay? And so that means that even further simplification, we have that this is just n choose n divided by 2 of 2 to the power n divided by 2 multiplied by I to the power n. Simply because -1 to the n over 2, that's the same thing as I square. Just distribute that out with the exponents, and so there we have it. So there, that means the residue is going to equal this for what is it? Even ends. So 0, okay, and so therefore that's our observation we have. So n is even. Let me also underline this just for here. Then if n is even, then that means the residue is going to equal this. All right, excellent. So now let's actually, we need to make a couple more, definitions in order to continue further, because this is actually going to be extremely important here. So we know that the definition of the binomial coefficients, I'll say n choose k, that is simply just equal to n factorial divided by n minus k factorial, then k factorial. Okay, what you'll notice is that, so that would have to mean n choose, we know that n choose n over 2. If we plug this all in and simplify everything, you notice that this is just going to equal just n factorial and then divided by n divided by 2 factorial square. This is actually very interesting because by definition, for the natural numbers, we have the swinging factorial of n is defined as the following. So the swinging factorial is equal to n factorial divided by the floor of n over 2 n factorial square, implying that for even n, for an even n, the floor of n over 2 is going to equal n over 2, and so therefore this is actually going to equal n factorial divided by n square, or n divided by 2, then factorial square. And so therefore back here, this is actually going to equal the swinging factorial of n. So we actually have a new substitution that we can actually utilize from here. And so the rest will be easy from here, because now that we actually make some establishments with both the odd and even ends, now eventually we can indeed apply the residue theorem. So I think also this is, actually let me write it like this. Since we said that this is swinging n, that's going to equal here, let me also write that this is the residue of f of z 0 for even n. And now we can continue making the calculations. All right, so now by residue theorem, we know that the contour integral of a function f of z, it has to be over a closed and a simple path. So, it like loops, in other words, and there's no intersection with each other within that path, another way to say it. So we know that the residue theorem says that, res theorem. So we say that the contour f of z dz over a path c is equal to 2 pi I, then multiplied by some index j for the residue of f of z, and then some pole z sub j. So here we only have one pole, and that's z sub j are the poles of f of c inside c, and we only have the pole z is equal to 0. Interestingly, because we have a unit circle with radius 1, that pole falls to inside that path, which means we only have one residue that we need to calculate, which we figure out by the observations that depending on the n and even numbers, they give out 2 different results, and that's what I mentioned earlier in the video. Also, it's worth noting that I wrote the swinging factorial of n, that's actually the coefficient. So we just plug this back in, then we'll get our residue of the residue of f of z at the pole 0 for even n. So this will be just plug 2 to the power n divided by 2, and then multiplied by I to the power n. So now the last thing is just, now we just got to apply the residue theorem, which simply just uses formula. Then we have the following. So this will be I, then multiply with I is equal to, and then we have 1 divided by 2 to the power n, then I to the power n plus 1, multiply by 2 pi I, and then multiply with the residue of f of z at the pole 0. Okay, and then we just gotta calculate those two different values we achieve, and then we'll be good to go from here. So lastly, so for odd n, then I is equal to 1 divided by 2 to the power n, I to the power n plus 1, multiplied by 2 pi I times 0. Of course, that's just going to equal 0. Then lastly, for our even terms, so for even n, then I is equal to 1 divided by 2 to the power n, then times I to the power n plus 1, multiplied by 2 pi I, and then plug this back in for that residue for the even. So this is just the swinging factorial of n, then times 2 to the power n divided by 2 multiplied by I to the power m. If we simplify all that out, then we are indeed going to get this following: the swinging factorial of n, and then multiply by 2 to the power 1, subtract n divided by 2, and then times pi. So there we have it. We actually have our final two answers. And so this is indeed what it comes down to for our given integral. So thus I, capital I, is going to equal to the following. We have 0, and then we have the swinging factorial of n, then times 2 to the power 1, subtract n divided by 2, then times pi for odd n, and then for even n. And just like that, we are done. It's this was a pretty fun, you know, definite integral to work on. But of course, yes, you can use the reduction formula to actually compute this integral itself without having to do all this. But I think this was a pretty neat twist to, you know, approaching things from another perspective. And if you were to plug the values for positive n's into Wolfram alpha, you'll actually get, you know, these following results, assuming that whatever numbers you plug in for positive integers. So that's great. And yeah, it's pretty cool if you ask me.